Started recording. So we're going to talk about the errors that are generated in computation by computers. So normally we tend to overlook these errors. We tend to trust the computers in a way, but we shouldn't. So we should be aware that computers are deterministic, yes. They're pretty precise, but they're inexact, okay? They don't perform exact mathematics. So if you solve a problem, okay? Let's say you solve, well, any problem. So you're programming, your software is solving some problem, right? And maybe it's a highly mathematical problem. You have lots of formulas. You cannot just copy and paste your formulas in your code, okay? And trust the computer to carry out the instructions you code in the formulas and give you the exact answers you were expecting. It doesn't work like that. So sometimes compilers can help us reduce the error that builds up with doing arithmetics in computers, but sometimes they don't help because, of course, compilers cannot read our minds, right? So I want to open the lecture with a very philosophical talk from artist Ali G and well, some scientists. I don't even know who they are, but the conversation is quite interesting. And okay, let's have a look.
Science. What is it all about? Technology. What is that all about? Is it good or is it whack? There's a bloke from around my hood, Staines, called Rainbow Jeremy, who reject everything to do with science. He just chill at home, he smoke his own homegrown, and check this, he don't have a telly. And shit, he don't have a telly.
Yeah, he lives in a house though.
Yo,
that house is a product of technology.
No, he ain't got no technology. You can check out his website. He ain't got no
house itself.
He wears clothes, shoes, he eats food.
As computers made our lives better.
I don't think there's any question about it.
Will computers ever be able to work out what 999999999999999999999 multiplied by 9999999? Yo, I ain't finished. You don't know what I was going to say. 998999999.889 9889999999999.
The answer is yes.
The most powerful computer in the world today does 36 trillion operations a second.
So would it be able to multiply 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, yes. You don't know what I was going to say. Multiply, you don't even know. 10, 10, 10, 10, 10, 11, 11, 12, 13,
whatever numbers you name,
89, 20, 100, 100,
yes.
million.
Yes.
Thousands,
yes.
Million.
Yes. Whatever numbers you want, you will be able to multiply.
0.99998.
Yeah.
Without blowing up.
Yes.
Yeah.
Okay, so who's right? So will computers ever be able to multiply 999999999999999999999 by 9999998999988999999999999? Sorry?
Sorry.
Oh no, I didn't rehearse that. I surely missed some lines, but it makes for good performance, right? So, so the answer is yes. And so the scientist says the answer is yes. And the other scientist says the most powerful computer in the world today does 36 trillion operations a second. So it doesn't make any difference. Whatever numbers you name, a computer will be able to handle it. Whatever numbers you want, it will be able to multiply. So is that true? Is that true though? Okay, by show of hands, who sides with LEG? Okay, who sides with the scientists, guys? Okay. You don't side with anyone. You're okay. So, well, we can test this hypothesis. So, we can multiply these numbers and see what happens. So let's play science. So yeah, I actually wrote down the numbers. And let's run the code. Here I'm using two things. I'm using the usual 64 bits float, the one you normally use in calculations. And I'm using a library for Python called decimal, which lets you specify a custom precision for your operations, right? So I set the precision of the decimal library at a really high value. That didn't have to be that high, but and I actually performed the multiplication with floats, and then I performed the multiplication with the decimal library, which is more precise, right? And as it turns out, the float multiplication is actually pretty wrong. Can you see these numbers? So okay, we have a very, 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 very long number, a lot of lines, but our error is quite big. Okay, so maybe LEG wasn't that wrong, meaning that okay, of course you could argue you still use a computer to perform this multiplication, just change the library. Well, that is true, but so the arrogance which the scientists used in answering LEG stems from two factors. So the science guy was probably thinking, well, of course, a computer can multiply any number you can come up with. Meaning that there's so much representational power in the computer that there's no problem multiply any number you can come up with. And that is wrong as well. Okay, let's say we don't use the float representation. Let's say we build our representation. I mean, we have lots of space in our hard drive, and we can come up with an algorithm to deal with another representation of our numbers, of our real numbers, okay? So let's come up with another representation. Well, but as we know, there's a finite number of bits, okay, available for representation in a computer. That means that you can't multiply everything you want. So you give me your representation. So how do you actually represent numbers in your hard drive, let's say? And you give me the space you have in your computer, and I'll give you a number which you cannot, for example, multiply by 2. I don't know. I can give you numbers you can't treat with your computer. And of course, okay, the second fact, which is you can argue against. So the other. I'll assume some intention here from the part of the scientist guy. So I think that his thought process was that our normal representations of numbers are very good, are good enough, so that you cannot come up with a number with numbers you can't multiply, and that I showed you is completely wrong, right? I wrote down the numbers, and we have huge errors with our usual representation for real numbers, which is the float, okay, the floating point representation. which now is usually 64 bits on our computers, right? Well, at least, well, yeah, normally it is like that. So, of course, you could also say, well, okay, maybe our floating point representation sometimes doesn't work very well. You cannot work with some numbers. Maybe you can just make up your representation every time you need one. So let's say you're working with really big numbers. Well, you just create your own representation, you run your algorithms on that, and maybe you're happy. Well, it turns out it's not that easy, because of course our computers are optimized to work with that kind of representation, with the float 64, right? The IEEE 754 float, right? So what happens if you make up your own representation and you try to run your algorithms, like for example multiplication, on your representation? Well, this is already computed, but I compute it again. So I run a timing algorithms on the normal float multiplication and a multiplication with the decimal representation, the one I use to perform the actual exact arithmetic of those two numbers. I don't know if you can see very well. But here you have the float multiplication. Okay, it's inexact, but it is performed in 16 nanoseconds. This is probably not really accurate because a single float operation is really fast. So I don't know if this timing function is accurate enough to capture it, but we can have a comparison between order of magnitudes, right? So here you have nanoseconds, and with the decimal representation, we have microseconds, which is 1,000 times more. Okay, so it's 3 orders of magnitude greater. Okay, so it does make sense using floating points for your operations, because your processors are built to deal very well with those representations. Okay. So, I know you did a little bit of a data representation thing last year. So I want to look at the floating point representation from a slightly different point of view. So I will give you a refresh. Okay, I'll review a little bit what a floating point representation is how it works. But I really want to show you a visual representation of what this means in practice, okay? So, what's a floating point representation and why is it built? So, the floating point representation is one of the ways you can represent real numbers, infinite strings of bits, okay? So the problem is, of course, your computer, the only thing that your computer can do, as we learn, is read those zeros and ones and basically rewrite them using some rule, right? And we learned that, for example, when we perform arithmetic on floating points, right? The result came out exact, or well, approximately the ones we would expect, because that representation works with the operations you define. So you say, okay, let's define a representation of numbers in these bits. So we say this bit means this bit means that. So you give your semantics to these strings of numbers, and then you define your operations that respect these semantics. Of course, from the side of the computer is just flipping bits and okay. But you give your semantics to the operation, and so in the end, the result of the operation reflects your semantics. And the number it spits out can be interpreted by your semantics because you followed your semantics all the way through, right? So, there are many ways you can represent these numbers. Why floating point? Well, the floating point is quite handy because you have an exponential there, and not only with the mantissa. That means that you can span a large range of numbers, right? If I were to use a fixed, well, okay, no, let's still talk about floating point. So you can represent the very, very small and the very, very large, right? The only drawback is that if you represent, for example, the very, very large, you lose some resolution, okay? Meaning that, for example, near the 0, you have a lot of numbers you can represent, but when you get the trillion, between one number and the other, you have a lot of real numbers you cannot represent, right? But that's all right normally. So, for example, if you do engineering, you see that all the time. If you're dealing with one order of magnitude, you tend to forget about the lesser ones. So if you're working with trillions, you don't really care about the 7th decimal place in your number, right? So that's okay. So I actually, okay, so you know how it works, right? So for example, for a 64 bits floating point, you divide the space, let's say, you divide the bits in 3 parts. One is the sign, so you have 1 bit which tells you what's the sign when you interpret it with your semantic, you know. So this is the sign. You have an exponent and a fraction, right? So that to actually get out your number, to interpret this thing and get out your number, all you have to do is take the bits of the mantissa, put them after 1 pointed. Okay, this is a normalized floating point, meaning that it is always assumed, but before the bits of the mantissa you have a 1. So it's 1 point bits of the mantissa in binary multiplied by 2 to the bits of the exponent, right? This is called a normalized floating point representation. So what I want to do now is, okay, you now know the theory. Okay, there's an exponent in there, there's a mantissa in there, but what does it mean really? Okay, it's very clear what it means mathematically, so you have a formula, you can apply that. But what does it mean intuitively? So what I wanted to do is build up, so code a little simulator. I spent the last 3 days in a vortex of programming to get the simulator working right. I still don't know. There could be some bug in there I didn't notice. That's actually highly likely. But I think the mostly it should work. So the results you will see will be exact, I think. So I build the simulator. What I do is just, well, I give you this file so you can have a look at the code. Or what I do is I create my own implementation of floating point numbers. Okay, so I have this my little float object, and what I want to do is build these numbers and plot them so you can see what numbers you can represent with this my little float, right? So I choose. So when I create this my little float, I have a sign, a mantissa, an exponent, and a bias. I won't talk about that. So for example, if I wanted to create a 64 bits floating point, I would have, okay, a sign, then the mantissa would be 52 digits, and the exponent will be 11. 1152 is 63 plus 1 to 64. But if I want to create my own floating point, I can have, I don't know, 4 bits of mantissa and 2 bits of exponent, right? That is perfectly all right number, floating point number. So I also want to be able to add two floating points with this representation. And why I want to do that? Well, I want to show you that when you add these numbers, you build up errors. I actually want to show you how that happens. So you can have a look at this code. So I think it could be useful to see how it works, like under the hood. I implement my own rounding function, which is used when adding. When you add two floating point numbers, at least what I do is, okay, take the number, take the other, add them in an intermediate representation, which has more precision, and then get that, round it down to the regional, number of bits in mantissa, number of bits in exponent, so the regional precision, and that's the output, right? And that is done a lot for a lot of operations on floats. I don't think that is done actually for addition, multiplication, division. I don't think it's needed, but that happens all the time with floating point. So, okay, now I have my now we have our floating point object. We can start creating our own floating points. So what I want to do is pick a number of bits in the mantissa, pick a number of bits in the exponent, and work out what numbers you can build. Okay. So create a huge array. Well, create an array, and inside that array you put all the numbers. And then I want to plot the numbers and show you how visually, intuitively, what numbers you can represent with floating points. So that's exactly what I do here. I have two for loops to build my numbers. Okay, here I build a user interface, doesn't matter. Button sliders, doesn't matter. And plotting, blah, blah, blah. Okay, so should be able now to run everything. And okay. So I initialized the whole thing with 2 bits in the exponent and 3 bits in the mantissa, right? And this is all the numbers I can represent on the real line with my choice of exponent and mantissa. Now I'm going to manipulate that so you see how the represented numbers change, right? So I put 3 representations. Okay. One is the normal, the normalized floating point. So you see that the expressive power, the representational power, so you have many more numbers near the 0. Then you start having less and less and less and less and less, but the range is quite high, right? So you can, okay, here you can get to 4 because the exponent bits and the mantissa bits are low. But you see, if you had these, if you had the same kind of resolution here, here, as you have here, you will get probably to here, right? You couldn't represent big numbers. So I colored each one of these parts differently because each part is different from the others from the exponent. So inside here, you're changing the mantissa. So you maintain the same exponent. Then you change the exponent, and you get to bigger numbers, of course, right? Because of the exponent. But because you change the exponent, your resolution is exponentially lower. Okay, so as you get higher and higher numbers, you get more spaced numbers. Okay, see that? Then you have the normalized floating point. So the normalized floating point has always a 1 implied before the mantissa, right? So you have 1 point mantissa. And that means that, for example, if you have for example, you can never get a 0 if you don't actively decide that a certain combination of exponent and mantissa is a 0. That's what the IEEE float does. So you say, okay, this number here you interpret as a 0, this number there you interpret as a plus infinite, this number there as a low, a minus infinite. But with a normalized floating point, you actually, if you stick to the numbers you're representing, you don't have a 0, right? To get a 0, you have to denormalize. Why? Because you always have a 1 point something. So 1 point something multiplied by some 2 to the exponent, let's say you have 2 to the minus 1, 1/2. So 1 multiplied by 1/2, 1 multiplied by 1/4, 1 multiplied by 1 to the 8th, sorry, 1 on 8th, right? You never get to 0. You get near that, but never to 0. And if you actually, you can actually cover that space by denormalizing the floating point. So you say, okay, the 1 is not implied anymore. You have a 0 so you have a 0 implied before the mantissa. That's something interesting to know. So you can see, right, that near 0 you have many values, and then get. Now what I want to do is add some bits to the mantissa. So what do you think would happen if I used more bits to represent the mantissa? I mean,
You get smaller gaps, so the range is the same, but you've got more sort of.
very, very good. Very, very good. Yeah, that's exactly what happens. Actually, the range increases just a little bit, because with smaller gaps you can get a little bit more here, right? But no, you're totally right. So I add a bit to the mantissa, and you see the space is much more dense. Here I put also the fixed point representation, right? So the fixed point representation is basically an integer, but you're implying that this integer is divided by some denominator, right? So what you do, for example, here, you cover all space uniformly, which could be good in some applications, but normally, as I told you, like if you work, normally when you work with problems, if you work near 0, okay, if you work with the big numbers, you don't want to know what happens in the lowest bits, okay? Meaning that even if you lose some of that information, nothing really matters, doesn't really matter. So we change the mantissa, and you see when you change the mantissa, you just, right, you add, you add more resolution to each chunk, let's say, right? Now, what would happen if I change the exponent? Well, you know, right? Exactly. So you get a wider range, and let's have a look at that. And of course, you get more chunks, let's say, right? So, okay. So you just saw what happened, right? The former floating point could get near 4, and here we can get near 16. Okay? And if I add another bit to the exponent, we could get to 256, more or less, right? And so here, for example, we would have very, 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 very good resolution near the 0. In fact, I want to zoom. Have a look. Okay. Well, you can see there's a lot going on near the 0, right? But when you get near 256, you don't actually have many numbers to represent, right? So if I were to, for example, here you have 100, let's say 100 initial numbers, so from 100 to 200, of course, so 100 integers. But here you have only 1, 2, 3, 4, 5, 6, 7, 8 representable numbers. 8, which would be 2 to the third, right? 3 bits. Okay, so I just wanted to show you visually what the exponent and the mantissa and the floating point representation actually mean, okay? Now I want to do some summation, okay? Now I want to tell you that because we're working with a subset of the representable numbers in a computer, meaning that you have the 64 bits floating point, right? All numbers that are here are a subset of the 64 bits floating point, because we're working with less precision in the mantissa and a smaller exponent. So all these numbers you can actually represent with a floating point, 64 bits, the normal one. So the nice thing is that because of that, I can compute this sum, right? And I will compute this sum, adding two floating points with my representation, so less precision, let's say, and check the same sum, but summing 64 bits floating points. So we have an exact sum, which is here the actual sum, and we have the representable sum. So the sum which is actually, which you can represent with these numbers, right? So, for example, here I do something that should never be done with floating points, which is add big numbers to small numbers. So visually now you can see why this is wrong. So let's move A a little bit. You see that? So if you add A to B, of course you get an actual number which is bigger, but you cannot represent that number there. Let's just go a little bit further. So you see, here there's no tick. You don't have that number in your floating point representation. You cannot reach that. It's not in the set of numbers you can represent. So what that means is that you're losing some information. So you should be here. Let's say somewhere very close to 3, but the number you can represent is actually a little smaller. And that, is that a problem? Well, it depends. It depends what you're doing. It depends on your algorithm. If you're smart enough, you can avoid this being a problem. Normally, not always. But if you're not smart enough, well, if you're not knowledgeable enough, if you don't know that this problem exists, this losing of information, you could write your algorithm so that all these small errors add up, and you get with a huge, you get garbage from your algorithm. So you get some number which is totally off. For example, if I had to, so I add B to A, right? And then again A, and then again A plus A plus A plus A plus A. I can do that here, right? What would happen if I did that?
The precision difference between
well, what would happen is exactly what's happening right now. So if I add an A, I stay there. Actually, let's have another A. Let's see if I can. Okay. Let's do like this then. I just want to show you something. Okay, for example, let's see if I can. Take again. Exponents here. Okay, for example, here maybe it's at 5.5. You see that, right? And I add a very small a. And because of that, nothing changes. I just stay in 5.5. Whereas the actual sum is 0.125 more, right? So I lose 0.125. If I had to do B plus A plus A plus A plus A plus A plus A, what would happen is I would stay there. I would stay there all the time. And I would accumulate that 0.125, right? And in the end, maybe, my actual results should be all the way here. But you stay there because you wrote your algorithm without keeping in mind that this floating point representation is just not magic, okay? It's just, your computer is not intelligent. We came up with a lot of tools to make sure that these kind of things don't happen. So as I told you before, the compiler can check if you do something like that, okay? At a very, so it's not smart enough to do it all the time, but sometimes it can, okay? But not all the time, and depending on the algorithm you're writing, your compiler could just not understand that you're doing that mistake, and you end up with big, big errors. So it's not like it doesn't happen. It happens all the time. It happened to me. For my PhD, I was building a simulator with neural networks. And okay, basically because I was working with differential equations, I had a lot of going back and forth between exponentials and logarithms, right? And they're not really precise operations. They add error pretty quickly, right? And I was getting results which were completely wrong. And hopefully, because I knew very well the problem which I was tackling, I knew they were wrong. So I was able to say, oh, something very weird is happening at the level of my code. But if I didn't know, though, I didn't know the problem, if I didn't understand the problem very well, then I would say, oh, okay, these are the results of my simulation. Okay. So I noticed. Many times you won't notice, okay? So you have to keep in mind that this can happen so that you have that critical eye on your code, that critical look and say, I have to pay attention to this, right? So it happens, I mean, everywhere. So have a look at this project.
Was taken. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, feu. Allumage. Décollage.
Something is This is the RN5, and I want to have a look again about what the rocket was doing. So straight. So it was going very well. At a certain point, it curves so quickly, and that, of course, at that speed, it curves so quickly that it just exploded, right? So the pressure on the body was so high that it just exploded. So what happened there? That is, it was a bug. So, okay, steering was controlled by the onboard computer, which mistakenly thought the rocket needed a course change because of numbers coming from the initial guidance systems. So you had some data from the sensors, from the initial sensors, and those were fed to the guidance system, right? So that device uses gyroscopes and accelerometers. The numbers look like flight data, bizarre, any possible flight data, but were actually a diagnostic error message. The guidance system had in fact shut down. This shut down, of course, 36.7 seconds after launch, when the guidance system's own computer tried to convert one piece of data from a 64-bit format to a 16-bit format. So basically you had an overflow. And the rocket was thinking that, I think the speed was, or the acceleration, yeah, I think the gyroscope, well, the acceleration, I thought the acceleration was much bigger than it was because of this overflow. And then the guidance kicked in, and the rocket took a sharp curve because, it's like, well, you have an overflow, right? That's exactly what you expect from an overflow. So it was straight, and at certain points, this corrupted data was fed in, and the rocket just thought, okay, I need to curve very, 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 very sharply now. And it completely destroyed the rocket. This is the RN5. And this happens, for example, in this Vancouver Stock Exchange. It's a stock exchange place, and they made an index to track how well it was doing, right? So at every operation, basically, they rounded down the index. And that means that the same error, so an error in the same direction was added every time, blah, 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 blah. So after a year, I think, from the year? Yeah, right? Yeah. So after a year, you had an error, which was basically the index was half of what it was meant to be. Okay, but the Vancouver Stock Exchange was doing really well, so they knew the problem, right? They knew the problem, and they said, "That's just impossible. How could the index be so low if we're doing so well?" So they managed to correct the mistake. Sometimes you can't correct the mistake. So, for example, in this Patriot misfit, right? Here again, you had another error you can do with floating points. Basically, you had a conversion from decimal to floating point. From integer to floating point. So they recorded the time in this missile. So this missile had to intercept another missile in count, right, to destroy it. So the Americans were launching this missile to what's the name of that? Scud. Okay. They wanted to intercept it, right? So of course the missile has to perform some mathematical operations, to actually say, okay, I'm here now. I'm going to in this speed. I will be there in that moment, right? So the time was taken in milliseconds, I think. No, in tenth of seconds, and that was then converted to a float representation. Normally, maybe it's not that big a deal, but when you're going hundreds of kilometers per hour, and your error gets not that much, so it was going very fast, and the accumulated error in seconds was 0.34 seconds. So it thought it was 34 seconds early, but that meant at that speed 687 meters off the target. Okay. So this Patriot missile, because of this conversion, never hit the Scud. The Scud hit the Americans and killed a bunch of people. And that was completely avoidable. But it was not, because these errors are often overlooked. And we accept them like a fact of life, but they shouldn't be. So now you're aware that this happens. Please don't work on missiles. If you do, remember me and my words, mark my words. So, okay. So, okay, you have to live with the error. But in our everyday life, you see that computers are pretty accurate, right? Okay, I'm talking about errors, but most of the time they seem to do pretty well, right? The algorithms run, the computer work, Your day-to-day life in software, it's usually pretty much bug-free, right? Why is that? Well, because a lot of smart people worked on ways to minimize the error, right? So, you have a problem, a mathematical problem. So you have a representation of the problem, you have a formula. As I told you, you cannot just copy and paste the formula on your computer, okay? When you translate that formula in an algorithm, you're doing an approximation, okay? So you're approximating the problem, let's say. You can measure error, of course, okay? What do you do? Well, so you have this problem, phi. How do you pronounce that in English? I don't know. Anybody knows how to pronounce that in English? Phi? It's PHI. Phi, okay. Phi? These Greeks. Okay, so you have your problem phi, and then you have your approximation, phi with a hat. Here, your modified problem, right? And what you can measure, of course, the first thing that stems, the thing is, okay, let's take the input and let's compare the actual solution with the solution of my algorithm. That's of course the first thing you think about doing to have a look at the error. And actually, that's exactly what I did in my in the sum thing I did in my simulator, and in the LEG multiplication, which is now a thing in mathematics. So let's call it LEG multiplication. So I measured the forward error. So the difference between the actual solution of my problem with the solution that my algorithm is giving, right? And you want to make sure that this error here is pushed to a minimum, okay? So it has to be as small as possible, and that's actually true. When we see, when we have a look at floating point operations, people have worked on them so much that now when you perform addition, multiplication, division, they're very, very, very precise as they can be, actually. Problem is, sometimes it's hard to quantify this forward error, okay? It's harder to analyze the way an algorithm maps your input to a slightly off output in respect to the real output, right? So, in fact, when people started to work on this error, on the quantification of the error, so when scientists started building computers, they were aware of this problem, of this numerical problem, right? The problem that your algorithms could make the error explode very easily, right? And initially, they were very pessimistic about the possibility of minimizing this error. We're lucky that Turing and James Hardy Wilkinson, they had a pretty neat idea. They reframed the question. Instead of saying, okay, how off is my output in respect to the output I should have? They reframe the question and say, okay, so my output is a little off, but for a not ill-conditioned problem, and I will say what that means in a minute, that output is actually the solution, the right solution, the exact perfect solution, okay, for a slightly perturbed input. What does that mean? Okay, you get some error, so you got a little farther from where you should be. Okay, your number is a little off, but that number maybe is the right solution to another initial value, right? So if you can quantify that, you can find how much distance you have between the two inputs, so the actual input and the input which gives the right solution, your solution, with phi, so the exact algorithm. So you can quantify that, and that's the idea of backward error analysis. This is really, really important. So you have to know this exists, right? So. Did I draw anything? Yeah. So okay, here we have the diagram, which could help you understand. So what this means is, okay, I have my input, and my imprecise approximated algorithm maps this input to some output, right? But maybe, so the backward error analysis says, maybe this output is actually right. So you can run your exact formula, okay? And, well, you cannot run in a computer, but you can do the computation maybe mathematically and get this result, okay? But with a slightly different input. And this is the backward error. So this should be the forward error, and this is the backward error. So you go backward and say, okay, this is the right solution, but to a slightly different input. So it's, on the other way. So is that the case? is that true in your algorithm? So the good thing about this is that the analysis is simpler. So you can run a backward error analysis, and that tells you if your algorithm is stable, backward stable, or not. And if the answer is yes, you're happy. Because what does it mean? It means that, okay, so your algorithm gives the right answer for a slightly different, different input. But that means that if you go to the actual input, you get a slightly different answer, which is all right. If we're talking slightly, that's all right. And that's true for problems that are not ill-conditioned. So there are ill-conditioned problems and not ill-conditioned problems, right? An ill-conditioned problem is a problem for which if you slightly change the input, you have big changes in the output. What will be an example of that? I showed you in the second lecture, chaos. For example, if you have a chaotic system, if your input is slightly, so if you have two inputs, right? And you run the equations, let's say, if you apply the equations to both inputs, you will have very, very different outputs in the long run. That's why chaotic behavior is unpredictable. That's why we cannot predict weather, for example, right? And that is an ill-conditioned problem. So you will run your backward error analysis, and that is no guarantee that, because it's an ill-conditioned problem, the backward error analysis doesn't give you anything basically of much use. So, but if your problem is not in condition, well, that's all right. You run your backward error analysis. You see how much the backward error is, and you say, okay, it's pretty small. So for a slight change of input, I get the right answer. That means that if I get the original input, I get a slightly different answer, and that's all right. That means that my algorithm is stable. So I don't introduce much error in my algorithm. I'm not that inexact. I'm still bounded, and that's good, right? And so that's pretty much it. So you have to be aware that a lot of algorithms were analyzed using backward error analysis and a whole range of tools from numerical analysis, that's what it's called, so that many algorithms are actually stable. So when you run them, you don't introduce much error, okay? And for example, each of the fundamental operations is backward stable, meaning that normally when you do addition, subtraction, multiplication, division with floats, for example, you have a very, 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 very small error in the order of magnitude of the machine precision, right? So, so what I want you to be aware of in this lecture, last lecture, the message I want to get to you is that the computers are really inexact, okay? And if you use them naively, because they're inexact, you will get your computation will be completely wrong, right? You will get easily big errors. So your computer is not this all-powerful God, as I tried to convey to you during all the modules. It's just a tool. And as a tool, you have to know how to use it. Now, the good thing is that many people worked on this tool, so you don't have to use the computer naively. Okay, the computer is set up in a way that most of the time these errors are just stabilized. And normally when you perform mathematical operations, you have libraries, okay, which are built to minimize, so your algorithms are stable. The algorithms you're using are stable. Okay, and there's a lot of smart people in the field of numerical analysis that make sure that your error stays low. Okay, but it's not like we reached the optimum. So we say, yeah, this is our computers do the computation as perfectly as they can. No, a lot of work is still ongoing, right? For example, last week last month, Seraphim sent me a paper from. Of course, I forgot because I didn't write it down. See. Okay, doesn't matter. This huge numerical analysis guru, which built a library to work with continuous functions numerically. Okay. Normally, for example, if you use a little bit of Mathematica Wolfram Alpha, right? For example, if you add two functions, let's say, what you do under the hood is symbolic manipulation, right? So under the hood, you have symbols for those functions, and that's what you do to get the final result, right? Like when you work with equations, right? And you make Wolfram Alpha solve your equation. Wolfram Alpha just try to combine the terms, and try to figure out. Okay, that's a way to do it. This guy made a library to work on this numerically. So he actually built the functions, the continuous functions, using high mathematics, which I don't understand. I try to know. So he builds the functions and adds them up. And the way he made the library, well, the way he made these algorithms, he showed that the resulting functions were really accurate. Okay, the error in doing this numerical treatment was very low, which is great because computers are so fast, the numerical solutions are often much faster, than the symbolic manipulation ones. And in fact, that's what he showed, that he could add many functions and get a really, really weird function, continuous function out of that with his approximations. And the error was very low, and he was able to do that in a split second. And it's hard to give you the idea of what this guy was doing. But what I wanted to say is that there's a huge field in numerical analysis of people trying to figure out how to make algorithms for computers that are stable. It's not a given. It's very, very hard. Okay, and if you decide to go into science, you will have to deal with this stuff. So, for example, in my simulation, I had to find a way to make my algorithm so that the error wouldn't explode, right? So that's something you need to do if you want to go in that field, for example, right? But even if you don't, you have to be aware that this is a thing. Really cannot remember the name of this guy. So I have good news for you. Okay, do you have any questions? None? Then I'll set you free. This time we just do 1 hour, and this is my gift for you.